Okay, I'm going to do a short lecture on how to use the ideal gas law. Because gases all behave the same, we can use a single gas law to describe all of their physical behaviors. If we know the pressure, the temperature, and the volume, we can calculate the number of moles of gas. And if we have any three of those variables, we can calculate the fourth. And I skip actually the historical view and just go to how to use it. Okay, so the ideal gas law, and by ideal gas we mean a gas that is not compressed and the molecules are spaced far enough apart that they are non-interacting. Once you get to a compressed state of gases, then the interactions must be accounted for. But for our purposes, we will always consider gases to be an ideal gas. The ideal gas law is PV equals nRT, where N is the number of moles of gas, P is the pressure in atmospheres or millimeters of mercury or maybe pascals. V is volume, and it's always going to be in liters. T is the temperature, and it must always be in Kelvin. And R is the ideal gas constant. And the units for the gas constant must match the units for pressure. So if your pressure is in atmospheres, you're going to use 0.0821 liters times atmospheres divided by Kelvin times moles. If you are using torr or millimeters of mercury, it's 62.4. And so just make sure that volume is in liters, temperature is in Kelvin, and that R must have units that are consistent with the pressure. Okay, so here's one example. How many moles of helium are required to fill a balloon to a volume of 10 liters at 1.25 atmospheres, and the pressure is at room temperature or 18 degrees C. 18 is pretty cold for room temperature. But basically we're solving for N, so we're going to rearrange the equation so that we divide both sides by RT, and then it becomes N equals PV over RT. And when you put in the number 1.25 for atmosphere and 10.0 for liters and divide by, we're going to use 0.0821 for our value of R, and we're going to add 273 to 18. And your number comes out to 0.523 moles of helium. Okay, now I want to do another example where I can show you in real time instead of using the PowerPoint. So let me screen share my iPad. Okay, so this is question number 64 in the back of chapter 11. And this question says, what is the pressure in millimeters of mercury when we know that we have 0.0115 moles of helium and the volume is 214 milliliters and the temperature is 45 degrees C. Now this is I like this example because it's going to make you change some of the units. So we start out with the ideal gas law, PV equals nRT. This time we're solving for P, so I'm going to divide both sides by V. So P equals nRT divided by V. N is fine. We can use 0.0115 moles of helium. R, now we're in millimeters of mercury, so we need to use 62.4 liters times millimeters of mercury divided by mole Kelvin. And temperature is going to be in Kelvin, and we have to add 273 degrees, so it'll be times 45 plus 273 for Kelvin. And then we're going to divide by volume. Volume has to be in liters. 214 milliliters is the same as 0.214 liters. So when you put everything in the calculator, what I get is 1070 when I take into account significant units. Significant figures, 1070 millimeters of mercury, which is a little bit over, it's like 1.3 atmospheres. So with this, you should be able to do a bunch of calculations on the homework. We use PV equals nRT when we have 3 of the 4 variables, and we solve for the remaining one. This is usually when there is one set of conditions that aren't changing. I'm going to go over next what happens when you have changing sets of conditions. And then, it's often used to get N. So it could be linked up with reactions. So maybe you have A plus B becomes C plus D, and one of these is a gas. So maybe you know the number of grams of A and it's the limiting reagent. You would go from grams to moles of A, just like we have before, and then from moles of A, you use the mole-mole ratio to go to moles of D. Once you have moles of D, you might be able to get pressure using PV equals nRT. So these can be combined with other things we have already learned.